Everybody, thank you for inviting me. Thank you, Francesco, and I find that this is a really amazing meeting. And my lecture will focus attention on the spherical aberration and the effects of visual acuity, contrast sensitivity, and the focus when we talk about multifocal IOLs. So, when we talk about spherical aberration, we have to know that it's a high-order aberration that describes the presence of a concentric gradient of power between the center and the periphery of the pupil. So we need to talk about a gradient. So the larger the pupil, the larger the amount of the measured spherical aberration that we have. So in most human eyes, look at the infinity, the measured spherical aberration is slightly positive. This means that when we delay the pupil, we have a slight myopic shift in our patient at the age of the pupil itself. And we have to focus attention that we can have positive spherical aberration in which the paraxial, that means the central rays, focus posteriorly with respect to the paracentral rays, and we can have the negative spherical aberration in which it happens just the opposite. The paraxial rays focus anteriorly with respect to the paracentral rays. And this is the result in both cases quite different from what we can have in a perfect system in which we have a precise focus. So, the spherical aberration can be defined as the useful aberration in the context of presbyopia correction, and manipulating spherical aberration can induce kind of multifocality, increasing peripheral focus, and increasing the possibility to get focus of images coming from far and from near. When we talk about spherical aberration, we also have to describe the shape of cornea, and we use the Q value, that's asphericity, as a factor that tells us how much and how the cornea is flattened in the periphery with respect to the center. So when we have a normal aspheric cornea, we have a Q factor that's between minus 0.2 and minus 0.45. When we have a Q value of 0, we are dealing with a completely spherical cornea. A Q greater than 0 means that we have a prolate cornea that happens after myopic refractive surgery. Otherwise, a hyperopic prolate cornea is considered to have a Q factor lower than minus 0.6. And this is how can we represent a normal cornea, in which we can highlight the values here, after myopic refractive surgery and after hyperopic refractive surgery. As you can see here, we have different optical zones and different corneal shape that can produce different Q factors. Let's go ahead. So this is the spherical polynomials. We already talked about them, and we know that the zeta Z40 is the symbol that describes the spherical aberration. C40 is the coefficient that describes the value that's expressed in micron units and is referred to a specific pupil diameter. So, the most important thing that we have to take into account is that the Z40 is related to the 4 power of the radial distance to the center of the pupil, and this is able to modify significantly the refraction of the patients. So when the refractive power, that's the divergence, is higher at the pupil center with respect to the periphery, we have a negative spherical aberration. Conversely, when the refractive power is lower at the pupil center, we have a positive spherical aberration. But when we talk about spherical aberration, we have to talk about also the longitudinal and the transverse spherical aberration. The LSA is the distance along the optical axis between the different ray intersection points as a measure of the amount of spherical surface. Otherwise, the transverse is the lateral extent of rays that intersect the paraxial image plane. So, this is very important, if the aperture stop to the system is reduced, so the rays furthest from the optical axis are blocked, then the LSA is so smaller. So we interact only with the central part of the cornea or central part of the optical axis. So reducing the pupillary diameter, only the paraxial, that means the central rays, are involved, blocking the peripheral one. So the plane of best image is then formed only with the rays reaching the cornea and reaching the retina, sorry. So when we have a positive spherical aberration, we have the lower vergence in the center of the cornea. Otherwise, when we have a negative spherical aberration, we have a myopic shift because only the central part of the cornea that has an higher power is involved in the optical system. And so playing with the spherical aberration, we can induce multifocality. So we can increase the amount of spherical aberration, and we can play with zeta 40 and also zeta 60 to manipulate the longitudinal spherical aberration and increase the depth of focus. So it's common that a negative spherical aberration is able to induce a negative myopic defocus at the center of the pupil, and reducing this myopic defocus toward the periphery. And this is what happens when we perform an hyperopic refractive surgery or when we perform a hyperprolate cornea by using a different shape of Q value for the cornea itself. And according to the previous image, this is how spherical aberration and longitudinal spherical aberration that you can see here modifies when we have a 4 millimeter pupil diameter. Let's see what happens when we increase the diameter of analysis. This is 6 millimeter pupil, and this is 7 millimeter pupil. So you can see here that we increase the LSA value, and it becomes higher and higher when we include peripheral rays. So remember that the spherical aberration is a gradient between the central and the periphery. So the central pupil zone power, what we mean when we talk about paraxial rays or peripheral rays? The central pupil power is an optical zone that refers to the 1.5 millimeter radius centered on the corneal vertex. Otherwise, when we talk about the paracentral power, it's an annular concentric surrounding area that stay over this, is an annular, oh, doesn't work, okay. It's an annular peripheral area that stay over this 1.5 millimeters. So why the spherical aberration is so useful for multifocal correction? We can manipulate it also creating a new shape of IOLs. For example, this is an impress, an Oya Vivinex impress IOL in which we have a central hyperprolate area. So we have a central myopic defocus error at the pupil center, and we have a paracentral zone in which we have a metropic refractive error. So when we focus attention, when we aiming at reading with the pupil constriction, we include only the central area of the optical zone, and so we can obtain a negative refractive error. Just the patient can be able to read. So when the pupil dilates, we increase the area involved in the pupil, and so we increase the far distance vision. Here, I try to describe in a paper published in 2009 what is the effects of spherical aberration on visual acuity at different contrast. And as you can see here, when all the aberration were corrected, contrast visual acuity is decreased by 7%, 36.8, and 53.5 after induction of positive spherical aberration. And this is what happens when we induce a negative spherical aberration. If we compare the results, the positive spherical aberration on visual acuity was less effective with respect to the negative spherical aberration. And this was true for high and low contrast condition. But the visual acuity does not increase when we only correct the spherical aberration. Otherwise, it increases when we correct the high order aberrations. And so it is not so important for the complexity of visual acuity. So when we have accommodation during near vision, we have a pupil constriction. As I said before, we can focus the image on the central near reading zone. When we delay the pupil, the reduced divergence at the pericentral zone allows to achieve a better and correct visual acuity for distance. And it's important to know that the negative spherical aberration must be accompanied with a selective central pupil myopia that's able to give us the multifocality of the eye. And this is how the lens is, the shape of the lens, and this is how it works. Okay. This is the same lens I told you before, the Oya geometric, the Oya Living X Impress. This is the ATDRS chart, and this is how the lens works. This is the refractive error, and these are the defocus curves. So this is what happens with this kind of lens when we have more than 4 millimeters pupil diameter. And this is what happens when we reduce the area of analysis. So this is 3 millimeters pupil diameter, and this is 2.5 millimeters diameter. And you can see here how the visual acuity improves and the defocus curves enhance in the near vision. And this is the comparison between the EDOF mono-EDOF lens with the same monofocal lens. As you can see, we have a different shape of the defocus obtained with the software made by Francesco. This is another lens which uses multifocality and spherical aberration to induce multifocality itself, and there's a combination between positive and negative spherical aberration that's able to increase the LSA, just to increase the multifocality. The same does the Bausch Smart, who plays with the 4-grade and 6-grade spherical aberration of opposite sides, just to increase the depth of focus. And this is the J&J Alliance mono-EDOF lens. This is how the lens works. This is the refractive error, as you can see. And this is what happens when we move from 3 millimeter to 2.5 millimeter. As you can see here, we have different shape of the defocus curve with an enhancement in the myopic shift. This is the brand new J&J Pierce lens. This is how the lens works. This is the refractive error, and these are the defocus curves. As you can see, when we reduce the pupil and when we reduce the analysis, the area of analysis, we have an improvement of the defocus for the near vision. And this is the same lens implanted in a patient who has had a hyperopic refractive surgery. So the two procedures have been combined together. You can see here the divergence at the center of the optical area, and this is how the lens works. So let's see what happens when we reduce the pupil diameter and we have an improvement of near vision. And we have a very...
1 second. Showing this is gonna break a lot of brains now. Give me a second. Have you confirmed this with a manually performed defocus curve?
Yes.
And does it fit?
Yes.
So right now you're saying that, and this looks like a pretty high hyperopic ablation, +4 or more, that a J&J negative sphericity lens in a post-hyperopic patient is able to fit well. This is a huge paradigm change, because before, with iHands, if you had done this, you would have taken that lens out.
Yes, we did this patient last week. It's a very new introduction.
Okay. Give it a few weeks.
More than half.
Okay? Because have you tried hyperopic LASIK with iHands mix?
Without, yes.
And are they happy with iHands and hyperopia before?
You say you implanted J&J without hyperopic?
No. We implanted some people with J&J lenses post-hyperopic LASIK, and they could not tolerate the fight between the spherical aberration of the lens and the spherical aberration of the cornea. They did not tolerate.
They do not match.
No, they weren't matching well.
Good results. It's a
Okay,
very
interesting.
Patients. They are really very happy.
Okay, we'll try.
A recent patient that we did last week.
Okay. Thank you. You now gave me an idea what to do next week.
I will tell you. And this is the real hyperpolate natural multifocal lens. Thank you.